So I think it's time and we can start the class. Just 1 minute. I think somebody's having trouble joining in. Just give me a minute. So today we will start with slightly more complex themes. And last time I had laid a little bit more stress on the concepts of game theory, how do you approach game theory and all that stuff. So this is a little bit, this just gives you a recap. There's a big lag in slides. Anyway, so is there an echo? Like, is there an echo? Yeah, there's some echo. 1 minute, let me just fix the echo. So I think there's a slight echo maybe because of the audio from the iPad, but otherwise I think it should be fine. Okay, so this is a little bit of a recap of what I covered last time. So we covered some notation and we discussed what is the best response to a strategy, and still an echo. Log off and log in. Sorry, give me 1 moment. Okay, so we covered the Nash equilibrium, we covered Pareto optimality, and we covered what are dominance strategies. And we discussed a little bit about notation, and we discussed a little bit about what we mean by best response. So today we will move on to something which is called the tragedy of commons. And it may not be fairly obvious right now as to why we call it the tragedy of commons, but as we progress through the game, you will understand why it's called. It's a very classic game in the world of environmental and resource economics. So this is the problem. It's a slight variation on the problem which is there in the lecture series. The problem is very simple and basic. There are two herds of livestock, and assume that they're both sort of using the same pasture. There's one big, grazing land or pasture land which is limited in quantity. So the pasture land is fixed. There's no way for the pasture to grow or increase in size or even to regenerate itself. So pasture is fixed, and whatever land it is, we have just normalized it to 1. So if the land may be whatever amount, whatever quantity, we have just normalized it to 1. So we have denoted that L equal to 1 or Y equal to 1. There are two herds with grazing intensity equal to x1 and x2. And x1 and x2, you can think of it something like, how much they can graze in a certain period or in a certain given amount of time. Right? So for example, like think about it in terms of, if there is a herd of goats and there is a herd of cows, the grazing intensity will be different for both of them, right? So x2 would, if it is for cows, would be more than x1, which is for goats. And now if you bring in another herd of elephants, grazing intensity for those will also be even much higher. So this is like the the subtext which goes into these kind of problems when they give you the intensity of grazing, or when they explain the amount of effort you're putting in to reap or mine or harvest something. All those are kind of same type of things. Now these type of problems are usually actually characterized in dynamic setting, like because all of these are time varying ideas. Like you're not grazing everything at one go, you will be grazing over a period of time. So most of these actual problems are mostly like dynamic problems, but for the sake of simplicity, we have just condensed everything into a simple simultaneous game right now. Assume that we're talking about one period over here, and in that period both the herds are grazing simultaneously. So this is the part where I think some people kind of get a little bit confused, but there's not really any need for confusion. Just assume that we have collapsed all the time into one period, and they're both grazing simultaneously. It is not a sequential move gate, it is a simultaneous move gate. In this problem, the one difference is that from as opposed to your lecture problem, there's also a cost. For example, like the two herds may have somebody who's looking after the herd, who's tending to the herd, or who's taking care of the herd while they're grazing, so they don't get into trouble, they don't get lost, whatever. Right now, there is a certain cost attached to that. So that cost is in proportion to, we can say, the intensity of grazing, right? So suppose, now it may not seem like very logical to you right now, but it is actually like that, because imagine if there is a bigger herd, the intensity of grazing would be bigger, right? So the person will probably want to charge more for it, so on and so forth. So you can say that the cost parameter C, which is a positive constant, is the same for both, but it varies with the intensity of grazing of both the herds. Cxi, where I is the number of the herd, I is equal to 1 and 2. Cxi is the cost associated with grazing. Now, apart from the cost, there is a benefit which each herd is getting, and that benefit is in proportion of its intensity of grazing, meaning intensity of grazing multiplied by whatever land is available for grazing, right? So at any instant, you can think of it like that. You can, at any instant, the amount of land available for grazing would be 1 minus x1 minus x2. So let's write this down. Let's formulate it as a game. So you can start with simple equation, herd and to graze with, say, intensity 1 and x2, right? So let's just simply write out the utilities, right? So if I'm writing the utility of herd 1, it will be u1, x1, comma, x2. And this will be what? x1 into 1 minus x1 minus x2, because x1 is the amount, you can say, which in one period first herd has grazed, and x2 is the amount the second herd has grazed, and none of these can be more than 1, of course. 1 minus x1 minus x2 is what is remaining, and in proportion of their intensity, whatever is remaining gives you the benefit. But there is also a cost this time. So there is a minus cx1 also over here. Similarly, if I write it for herd 2, it will be u2 x2 comma x1. Please take care of the notation. When you're writing the utility, you will write the strategy of the person or the player for whom you are calculating the utility first. Okay. So x2 minus x1 minus x2 minus cx2. So similarly, you get both of these. Now, what happens? What we do? Now, what we want to do is we want to actually maximize the benefit. That's what we always want. That's what we discussed in the first class itself, that we always want to maximize our utility or payoff or benefit. Not benefit, but utility, payoff, profit, whatever it may be, as the case may be in the given problem. So now U1 will be maximized with respect to what? X1 or X2? Respect to X1, right? Because for player one or for herd one, it can only control X1. It cannot control X2, right? X2 is something which it has to take as given. It cannot control X2. So what you will do is but remember, X2 is also varying. X2 is not fixed, but whatever quantity X2 may be, X1 has to develop a function for its best response to that particular quantity X2. What we will do is we'll want to maximize this. So we'll take a partial derivative of U1 with respect to X1. And you will get something like 1 minus 2x1 minus x2 minus c equal to 0. This is just simple differential calculus. And this gives you x1, you can say x1 star, if you want to call it as the best response, you can say x1 star equal to 1 minus c minus x2. If you want, you can do the whole derivative for u2 with respect to x2 also, but just by symmetry, you can also see that we'll get the similar kind of function. To start is 1 minus c minus x1. And here x2 and x1 can be anything. Right now, for Nash equilibrium, what we know is that at Nash equilibrium, both of the players will be playing their own best responses. So for Nash equilibrium, x1 star and x2 star will be the strategies, right? So both the equations solve each other, basically, in mathematical terms. Therefore, we can write x1 star, and instead of x2, we will plug in the value of x2 star, which we got, because both the equations need to be solved simultaneously. So x1 star is equal to 1 minus c by 2 minus half. x2 star is 1 minus c minus x1 star by 2. Now you can solve this. I mean, I don't want to spend a lot of time doing the algebra here. So if you want, you can take some time to solve it, but I'm just giving you the simplified expression here. Upon solving this, you will get 1 minus c by 3, which is very similar to the best response you got in the game, which we discussed in the lectures, which is without any kind of a cost. And by symmetry, you also get x2 star as equal to 1 minus c by 3. Therefore, equilibrium is x1 star comma x2 star equal to minus c by 3 comma minus c by 3. So this is fairly straightforward, more like a recap of what was discussed in the class, but in a slightly different situation. Now, the other question is this Pareto optimal? Now, this is a similar question to what we discussed in the class. So I'm leaving this for you to solve. I will post the solution for it after the class, like maybe in a day or two. But it will be good for you to solve this part, the Pareto optimality part, and check if this answer is Pareto optimal. If this strategy we have 1 minus c by 3, 1 minus c by 3, if it is Pareto optimal. Okay, so there's another question we have similar to the one which we were discussing on the tragedy of commons, and that is a slightly more interesting question. So I will move to that question now. Now there's a similar question. Say suppose there is a fishery. It is a fishery. In a fishery, there is an advantage in a fishery compared with, say, a pasture, that the fishery can keep regenerating itself. So say suppose you do not, extract all the fish from a fishery. There's only like, you only extracted, say, suppose some of it. So the remaining fish can still multiply, they can still grow, and they can still sort of regenerate and increase the population of fish. So now we are assuming that the fishery is of size y equal to 1. You can see this problem with y. If you want, you can solve it without y equal to 1 also. You'll get the same answer. It just simplifies the maths a little bit if you take it as y equal to 1. And we have a similar setup where there are two groups of people, two companies, you can say two firms or two people who want to extract or who want to fish in this fishery. And you can say that there is only one period or there are two periods. Either way, we are not taking it as a dynamic problem. So there is no need to get confused about first period, second period mentioned in these problems. I'm just trying to introduce you to all the different types of settings or language which you might encounter in this type of a game of tragedy of commons. So this particular question is taken from the book by Prajudatta, and this is an unsolved example. It's unsolved example 8.2. It's at the end of chapter 8. So if you want, you can go over it. This is an unsolved example, but there are some solved examples also. So now, in this particular example, what happens is that, whatever amount is not extracted, that is the quantity y minus x1 minus x2, regenerates, and it becomes under root y minus x1 minus x2. So in this, we have not assumed any costs. There are no costs, just to simplify. So what happens in this period? Now, let's see. And I want you to take this example to show how the case of a renewable resource is slightly different from the case of an exhaustible resource. So what we discussed earlier in the tragedy of commons is the case of an exhaustible resource. This is a renewable resource. So let's write the name of the game. We have a similar setup. I'm not writing all the all the detailed stuff about the setup in the notes again. Say fishery of size y equal to 1 and fishing intensity is x1 and x2, right? Now we'll again write the utilities of both the groups, say u1 1 comma x2 equal to, what will it be? Now this time it is going to be in proportion to the regenerated quantity of the resource, right? So it will be x1 under root 1 minus x1 minus x2. Because there is no cost, there is no cost factor cx1 here. And similarly, if you write u2, it will be u2 x2 comma x1 equal to x2 under root 1 minus x1. This is the main, it's very simple, but it's the main equation which you should be able to write. So a lot of these game theory problems will be mostly about understanding the language of the question and formulating it in the form of a game, understanding who are the players, understanding what is the strategy, and what is their utility. These three aspects of a game are what define a game. And that is, if you get that right, the chances of you getting the final Nash equilibrium are much, much higher. Because a lot of times people even mistake who the players are. And it happens. It's not something that uncommon. Again, what are we going to do? Now we'll again want to maximize u1 with respect to x1 and u2 with respect to x2. So we'll take a partial derivative as before, del u1 by del x1. Now this is 1 minus x1 minus x2 minus 1 by 2 under root minus x1 minus x2, right? And you're just taking a basic partial derivative, and this is equal to 0. Now, if you want, you can kind of simplify 2 minus 3x1 by 2 1 minus x1 minus x2, right? Minus x2, sorry. 2 yes, equal to 0. Now the denominator is a positive quantity because it's under root sign. It has under root sign. So what happens? It's going to be just the numerator we can equate to 0. Denominator cannot be 0, cannot be infinity. It's just a positive quantity. That means the numerator is equal to 0. X1 is equal to 2 minus X2. 3. You can say X1 star actually. Again by symmetry. X2 star will also be 2 minus X1 by 3. Nash equilibrium is when both equations solve each other. So you solve them simultaneously. X1 star 2 by 3 minus 1 by 3 into X2 star is 2 minus X1 star by 3. I have solved this. So again, I'll encourage you to please do the algebra yourself because I have already done the algebra and I don't want to take up too much of time just doing the algebra. So I'm just giving you the answer, but I would really prefer it if you actually solve it yourself. So the answer you get is 2 by 5. Or, in other words, you can say that this is greater than 1 by 3 or 2 by 6. Right? So X1 star in this situation comes out to be 2 by 5 means when the renewable resource is what you are actually extracting or when you are using, it so happens that because the resource keeps regenerating itself, game plays out in such a way that you will end up using it much, much more. Your intensity of utilization of that particular resource is going to be even higher. So the resource is going to get used up even more in the end. So, which is why the problem of renewable resource also does not come, the problem of renewable problem of a resource being exhaustible or renewable does not get solved when it is renewable. Because even when it is renewable, the best responses or the Nash equilibrium is such that the utilization or extraction of resources is even higher. And we'll study this, just one more example I will take for this so you get the concept. Let's just write the Nash equilibrium here. 1 star comma X2 star equal to 2 by 5 comma 2 by 5. Again, I'm leaving it to you to check the Pareto optimality. I think that is not very difficult. When you're checking Pareto optimality, what you want to do is you want to see whether the outcome is socially optimal, right? Pareto optimal means you cannot increase the payoff of both the players simultaneously by choosing any other strategy. And we do that by maximizing U1 plus U2 with respect to X1 and then with respect to X2. So when you solve for it, you will, whatever answer you get in a similar way, you will get the optimal answer or response. Okay. Now there is another question which is a variation of this question, which is the n player game. Now, say suppose there are n players in the same grazing problem. There's a lag. I have to refresh the screen. Okay. Yeah. So in this game, in the tragedy of commons, say suppose there are n players. And this example also I've taken from the Prajitatta book. But their formulation and setup of the problem is slightly different, so don't get confused. I have tried to model it and modify it a little bit for the problem I have taken in the class, the grazing problem. N players, say suppose there are n herds, it's a huge pasture, there are n players, there are n herds which are grazing over the same pasture. And you can say in the beginning, you can assume that you're trying to write the best response of one particular herd whose intensity of grazing is X1. And we're assuming that all other herds have the same intensity of grazing X. Okay, so in this question, what you want to know is we want to find out that how is it possible that this leads to the complete depletion of pasture and it is completely not very optimal. In the n player game, you actually understand why it is called the tragedy of commons. Now, let's write it in the same way. Say, suppose your the intensity of grazing for a particular player is X1 and or Xi. Say intensity Overgrazing or herd is xi. So we write the utility of xi comma x minus I fashion. And what we want to do is we want to write it first, just keeping it as xi, and then just to simplify it and to see what happens, we will assume that all x's are actually the same. So you will take this as I into 1 minus n minus 1 to x, where x is the intensity of grazing of all other players. They have the same intensity of grazing. So out of the n players, you are xi, my intensity of grazing, say suppose, or my herd's intensity of grazing is xi. For all the other n minus 1 herds, they all have x as the intensity of grazing. So, sorry, this is going to be 1 minus x. So the term in the bracket has to include 1 minus the intensity of grazing of all the herds. So n minus 1 into x minus, which is my intensity of grazing. Now say suppose we want to solve a symmetrical problem. If the problem is symmetrical, which we are assuming it is, we'll take xi equal to x, right? So now what do we get? You just say, let's say just u instead of ui or u1 is equal to x minus n minus 1 x minus x. Right now we maximize it with respect to x del u by del x. Solve the we solve this whole, it becomes 1 minus 2 n minus 1 minus 2. Correct? To x. Distance multiplied by x. So minus 2x equal to 0. This 2x, no wait, I've made some mistake here. So what did we do? 1 minus n minus 1x minus x. That is correct. So this becomes, let's just simplify here. 1 minus nx minus x. We want to just simplify it further. Nx squared minus 2 u by del x minus 2 n x minus. I think this will also be the same kind of answer. What you get is 1 is equal to 2. I will do the algebra again, but there may have been some mistake in the original question. No, I was doing it correctly. 1 minus 2 n x times 4x equal to 0. So 2n plus 4 equal to 1 by n plus 2. So you can simplify it further if you want. I mean, you can, there's not much simplification here, but basically you see that x is now, coming out to be 1 by 2 n plus 2. Earlier we were getting it as if you plug in the values of n, you were getting it as something else. And if you further simplify it, you can see that the resource, say suppose the remaining resource, we calculate how much remains. is equal to 1 minus nx, right? Because there are n players, they're all consuming with intensity x. So is equal to 1 minus n by 2n plus 2. Now, if we take the limit of n tends to infinity, we will get this as, not getting it as, okay, I will look at my calculations. I think I've made a mistake somewhere and I'm not able to find it right now. It's probably a very small problem. But this is the basic approach. It's some algebra which I think I have messed up, and I don't want to kind of keep spending more time on that. This is how you approach it, right? If you want, you can solve it without taking it as symmetrical, but in the end, the result you will get will be the same, even if you don't take it as a symmetrical kind of a problem. So, any questions so far? Questions? Okay. Okay, so we will move to something we discussed. I think we discussed in the last class, but it's anyways there in the lecture classes, in the lecture notes. So let's discuss the chicken game. From here, we will move towards something we call as mixed strategies. So a chicken game is a very simple game. In which, say, suppose there are two cars on a road, and they're both driving towards each other, and the whole game is about who gets to go straight and who gets to swerve, right? Now, obviously, if both the cars cannot go straight. If they both go straight, they're going to collide, and their payoffs will be zero because they will both meet their end. So the payoffs for straight are 0-0. Now, if the other guy is swerving, what would I want to do? I would want to go straight, right? Why will I swerve? So the payoffs for straight swerve are 3-1. And if the other guy is going straight, I want to save myself, so I'm going to swerve. So this is, the payoff is 1-3. And if they both swerve, they both save themselves, but they have a little bit of inconvenience, so the payoff comes out to be 2-2. So this is what we call as an anti-coordination game, which is sort of like the opposite of a coordination game. And in this, let's see what the best responses are going to be. So if P2 is going straight, for P1, the best response is swerve, which is, I've highlighted it, is your best response. If P2 is going to swerve, P1 is going to go straight, right? Now, if you look at it the other way around, if P1 is going straight, P2 is going to want to swerve. That's the higher payoff. And if P1 is going to swerve, P2 is going to go straight. You can see that if we just ignore anything called mixed strategy or anything, then the Nash equilibrium comes out to be straight swerve, swerve, straight, right? That is the Nash equilibrium. Because these are anti-coordination games, I want to do the opposite of what the other person is doing. It's a symmetrical kind of a setting. We want to see an alternate scenario in which, you don't know what the probability of the other player doing something is. For example, in this kind of a setting, if you kind of know the car owner or something like that, you may have a guess, or you may have some idea about whether that guy is going to go straight or is that guy going to swerve, right? You may have some sort of a belief. So for example, if you're sure that the guy is going to go straight, you will definitely swerve, right? Or if you're sure that the guy is going to swerve, you will definitely go straight. That's what the Nash equilibrium tells you, right? If the other guy is going to swerve, I will go straight. But what happens in a scenario where you don't know what the probability of that might be, of the other person's actions might be? So in those kind of situations, we switch to something called a mixed strategy. So the screen is again stuck. Yeah. So we will look at this mixed strategy games in this rest of this class, and a lot of these games are basically like like normal games which we may have looked at till now, like Battle of Sexes. The previous class I gave humanities versus sciences, rock paper scissors, many such games which are basically not really the best suited in a pure strategy setting. And we're going to look at when it is better for a mixed strategy game and when it is better for a pure strategy game. Now, the common sense tells you that if there is, say, a dominant strategy in a game, like any game, if it has dominant strategy, strictly dominant strategy, what does it mean? That irrespective of what the other player is doing, my strategy, this dominant strategy, is always going to give me a higher payoff. That is what dominant strategies are. So then I don't need to really worry about playing a mixed strategy because I already know what to do. Right? Whatever the other person may be doing, I'm going to play my dominant strategy. So even if I don't know what the other person is going to be doing, I still need to not worry about it because I don't need to guess, I don't need to calculate. I'm just going to play my dominant strategy. But in situations where there is no dominant strategy, like in this particular chicken game, there is no dominant strategy, right? As you saw that, it's an anti-coordination game. So whatever the other person is doing, I'm going to do the opposite of that. So there is no dominant strategy. And in such a game, you will choose a mixed strategy, which is a combination of the two strategies available to you. And what do we mean by, combination? That's the third point I mentioned, that you will just randomly pick any out of the two strategies. When are you supposed to do that? When there is a certain probability of, the opponent or P2 playing one or the other strategy. So say suppose there is certain probability P of the other guy swerving. I don't know what this P is right now, but there is some value P of the probability of this guy swerving. That is my belief. Okay, this is not based on some statistics. It's not a frequentist view or something. This is just my belief about how likely is my opponent to swerve, for example. So then if that, for a certain value of P, we'll just calculate it soon enough what it is, but that certain value of P, I am indifferent to choosing straight and swerve. I will just randomly pick one of the two because the mixed strategy is going to give me a better payoff than at least one of the pure strategies. So I hope this part is clear, that when are the players going to choose a mixed strategy and why will they choose a mixed strategy. Okay, before I go to the next game, let me just explain this game a little more. This is now, say, chicken game. Leave some space for this one. Now this is, say, straight. This is swerve. Straight. This is swerve. This is P2. This is P1. That's the game. Okay, so let's just mark the Nash equilibrium in the pure strategy first. All right. Now, let's say that the probability of P2 swerving is P. Okay, this is why I'm going to mark it. Belief of P1 about P2 swerving P. Okay, this is my belief. I'm P1, so suppose. Okay, so then what I'm going to do is I'm going to calculate my expected payoff. Now remember, when I'm calculating my expected payoff, I'm doing that basis the probability of the other player doing something. I am not uncertain. I'm randomly picking, but the probability is always going to be of the other guy. Okay, not of mine. Many people make this mistake. So when I'm calculating the payoff of P1, I will write this as expected payoff U1 of P1. Say suppose I calculated for straight strategy straight. It is if P is the probability of swerving, 1 minus P is the probability of going straight. So this is your expected payoff. And let's calculate it expected payoff of 1 for swerving. So this is 1 into 1 minus p plus 2p. Okay. So in the case of a mixed strategy, I'm indifferent between choosing straight and swerve. What does it mean that I'm indifferent? It means that the payoff from both the strategies is expected payoff from both the strategies is the same. So what I'll do is I'll do EU1 for straight is equal to EU2 for swerve, which is 3p is equal to 1 plus p, right? So this is p is equal to half. Okay, this is fairly simple. So what happens that when the probability of the other guy choosing swerve is like half, there's a half chance that he may choose swerve or straight, then I'm just going to randomly choose to swerve or to go straight. Now by symmetry, if you want to calculate it for P2, if we go by symmetry, and if Q is the probability P1 swerving, we will get P1, sorry, Q is also equal to half. This is only because this is a symmetrical game, not otherwise. There are many games, and we'll discuss some of them, which are not symmetrical. And you should not do this in games which are not symmetrical. What do I mean by symmetrical? That the payoffs are almost the same for P1 and P2 for similar strategies. So in this case, what we write as MSNE is first you write the strategy of the first player. So straight by 2, swerve by 2, and then of the other player. This is just the notation. How we write it, what we mean by 1 by 2, 1 by 2 is that straight into the probability, which is 1 by 2, swerve into the probability, which is 1 by 2. In this case, it is half, so both are half. Sometimes it can be 1 by 4, 3 by 4, things like that. So that's how you report your answer. Okay, so the questions I'm discussing today for mixed strategies are going to be a little bit more, higher difficulty level, you could say, than what we discussed last time and than what is there in your assignment. But it will help you in your assignments, and I think it would be pretty straightforward after you do this class. Now we go to a very popular example, which is the example of squash. So I don't know if anybody else plays squash here, but I play squash. And the game I have taken, the game table I have taken is again from the Project Datta book. And the payoffs here are written like so. Okay, so you may wonder why it is written like this. That is because this is a constant sum game, or at least it is characterized as a constant sum game. Right? If you want to write it as a utility and you define your own utility, then it can be written in a different way. But the way this is given in the book and then how it is commonly used is like this. And what we do in this kind of a game is that you need to rewrite this game to write the payoffs of both the players. In this particular game, if you read the language, you will understand that he is writing all of this only for T1. Assume you are T1. So what happens is, if in this game of squash, if you are starting a rally, say suppose you are hitting a shot, and you have the choice of hitting to the front of the court, or you have the choice of hitting to the back of the court. Right now, what you ideally want to do is that if you are hitting at the front of the court, you want your opponent to go to the back of the court, because that's how they're going to miss the shot, right? And they are in some place from where they can go to both the places, right?
So whenever you're hitting your shot, you always want to sort of maintain some element of surprise, some element of maybe some bluffing, some deception, something, so that the other person miscalculates. The other person kind of, instead of thinking that they should go to the front, they go to the back. And remember, in squash, it's a very fast game. So even though you can say that, you are playing first, they are playing second, actually all of these decisions happen within fractions of seconds. So you cannot exactly say that who is going first and who is doing next. It's almost like it is simultaneously decided. Okay? So what happens is that you have this kind of a game table. Now what you want to do is you want to know how often should you hit to the front of the court, how often should you hit to the back of the court, and you need to decide this based on some belief about the other player, how likely are they to go to the front or back of the court. So you are going to decide which one you should pick based on the other guy. So let me write this table again here. So let's go to game squash. This is 0.2, 0.8, 0.7, 0.3, but we want to write the payoffs for both the players. So this is going to be the payoff of both the players. This is because we have mentioned that this 0.2 is the chance of you winning the rally. So if your chance of winning the rally is 0.2, then the chance of the other person winning the rally is 0.8, right? If you hit to the front and the other guy also goes to the front, they have a higher chance of winning the rally, which is 0.8. So it's easier to write out the payoffs like this, because sometimes you may end up, if you're in a hurry, you may just end up taking the wrong payoff. And even though in your assignments this is not given like this, but it's a good idea to understand how to work with constant sum games. Now let's do the usual thing we do. Say suppose we take the probability of the other guy going to the back as P, right? If P is probability of P2 going to back of court, we have expected payoff of player 1 from playing the strategy small f as, so his payoff is 0.2 into 1 minus P plus 0.8 P. And similarly, we calculate the expected payoff of P1 from going to the back of the court as 0.7 into 1 minus P plus 0.3 P. Okay, is that clear? Probability of F, capital F into payoff from capital F, probability of capital B into payoff from capital B. This is for the strategy small f, and for the strategy small b, probability of capital F into payoff from capital F, which is 0.7, probability of capital B into payoff from capital B, which is 0.3. This is what I've written out. This is just basic probability and statistics and calculating expected payoffs. Now, for a mixed strategy game, for mixed strategy, at some probability P of the other guy, so suppose I'm playing against somebody and I am just trying to calculate at what probability of the other guy going to the front or back, I'm indifferent between hitting to the front or back. Right? That is what we want to find out. For a mixed strategy, EU1 F is equal to EU1 small b. Okay, so I'm going to equate these two equations now, or let me simplify it first. So this is 0.2 minus 0.6p is equal to 0.7 minus 0.3. that correct? This is plus 0.6. Yes. So now I bring P this side. This becomes P 0.7 minus 0.2 becomes 0.5. So in this case, again, it turns out that P is 0.5, or you can just write half. Right? So if the other person is equally likely to go to the front or back, I will randomly decide to go to the front or to hit the shot to the front or the back. Now we want to do this the other way around also, because this game is slightly different from, say, your chicken game. Now assume of P1 going forward is Q. Okay. Belief, or you can say, instead of probability, like probability is not accepted as a technical in these situations. So I'm just writing belief, which is the correct term here. Assume that the belief of P2 about P1 going forward is Q. Then we will do the same thing. We'll calculate payoffs of expected payoffs of P2 in both the scenarios. So let's say EU2 for going forward is what? 0.8 into Q plus 0.3 into 1 minus Q, right? And say expected payoff from strategy B is 0.2 into Q plus 0.7 into 1 minus Q. For mixed strategy, we do EU2 capital F is equal to E capital B. And now we just simplify this. We can first simplify this part. This is 0.5 Q. So we bring this side, and this becomes Q is equal to 0.4 or 2 by 5. So you see, this time it is not the same answer. Q and P are different values. So I would encourage you to also solve these questions so that you can go through the exercise of figuring out, how do you calculate the mixed strategy. So in this case, we're getting a separate answer. So what will happen? We'll get a separate, different response or different best response scenario, you can say, for MSNE. SNE is now equal to, so we wanted to do the, for the player 1, right? Now for player, this Q is for who? Q is for player 1, right? And Q is the value of belief for Q or for P1 going forward. So it is 0.2 to 2 by 5. You can simplify it later. I'm just writing it as it is for now. To 3 by 5. And sorry, why am I writing 0.2, 0.3? F and B. F into 2 by 5, B into 3 by 5, and this is just F by 2, B by 2, because P came out to be half. So capital F by 2, capital B by 2 is for player 2, but Q came out to be 2 by 5. So for P1, it is 2F by 2 and 3B by 5. 2F by 5, sorry, and 3B by 5. So what I'm writing is the Nash equilibrium strategies. By mistake, what I was writing earlier was the payoff at the Nash equilibrium. So if you want, you can write down what is the payoff at the Nash equilibrium. I don't think that's very difficult to do. You want to calculate what is the payoff at mixed strategy Nash equilibrium. You will do what um, what I was doing. To make strategy Nash equilibrium, you will calculate EU1 or EU2, or sorry, EU1F or EU1B, because both are the same, right? That was the whole idea. So you can write the payoffs, point 2 into, let's write this down. This is for player 1, and for player 2, it is 0.8. No, wait, sorry, not like this. I've sort of shortened it a bit too much. You can write it like this actually. Let me correct this. So EU1 F and EU2 capital F. You can write EU1 B capital, EU2 capital B also if you want, but at the end of the day, they are both the same. So now, given the values of P and Q, you can compute EU1 and EU2. So what is EU1? From here, we can see EU1 is 0.2 into 1 minus P plus 0.8 into P, right? You can compute it like that. 0.2 into 1 minus P, that's 3 by 5, plus 0.8 into P. This is EU1, and EU2 you can calculate as 0.2, or you can say 0.8 into Q. Sorry, this is not 2 by 5, this is half, because we're calculating P and Q. Remember, Q figures in the equation for player 2, and P figures in the equation of player 1. So this is 0.8 into Q. Now Q is actually 2 by 5. Plus, what is the equation? 0.3 into 1 minus Q. This is 0.3 into by 5. You can simplify this and find out what is the payoffs at MSNE. This is not usually asked, but I think they've asked you this somewhere in your assignment, in your submission. So this is how you will calculate. First, you calculate the values of P and Q, and then here, these equations, you plug in the values of P and the values of Q to get the expected payoff. In equilibrium, the expected payoff from both the strategies is going to be the same. That is why it's a mixed strategy. And you have to remember to use P and Q correctly. Like I was just, in a hurry, you can make a mistake. The P value is coming from player 2 and Q is coming from player 1. And P is going to figure in the payoffs of player 1. Q is going to figure in the payoffs of player 2. Sounds confusing, but it's kind of like something which becomes your intuition once you do a lot of these type of questions. So this is like a very simple 2x2 game of squash, which we discussed. And the question I think in your assignment is for a slightly different game, but I think it's a penalty kick game. We'll come to the penalty kick also. But this is like a similar kind of a setting in which you apply the same kind of concepts. Okay, so I will take a 5-minute break here. And in the meantime, if you have any questions, you can of course post in the chat. And after this, we will discuss the game of rock, paper, scissors, which we had discussed the last time. We didn't kind of find any equilibrium because it doesn't have any pure strategy Nash equilibrium, right? So we will now see how do we tackle these kind of games which don't have any pure strategy Nash equilibrium. So I'll be back in 5 minutes, and in the meantime, you can see if you want to try solving this question.
Okay, so I was trying to solve the echo problem actually in the meantime, and I think I might just have solved it. So I'm not getting an echo now. Hopefully, you're also not getting it. We share screen. So much better. Okay, so I will continue with some more, slightly advanced games on um, strategies. And if you actually go through all of these games, you are unlikely to have any trouble with your usual, assignments and things like that. Now let's look at the game of rock, paper, scissors. And if you see, this is the game we discussed in the, in one of the previous classes, where we had trouble finding any dominant strategy and we had trouble finding any kind of a Nash equilibrium. Just the dominant strategy, there was no Nash equilibrium, pure strategy Nash equilibrium. And if you remember, at that time, I had actually said that there is no pure strategy Nash equilibrium because there is, as we will find in some time, there is mixed strategy Nash equilibrium. So let's work on this and let's write down the table first. So this is the game of rock. Okay. Now, whole beauty of this sort of a game is usually that this is a game if in which if there were a dominant strategy, everybody would just play the dominant strategy, right? Because you want to always surprise the other person. That is what the game relies on essentially. So let me just write down the game table and see how the mixed strategy works in these type of games. Also, in a sense, sort of like an anti-coordination game. Or scissors. This is 0, 0. Rock cancels out. Rock covered by paper, so -1, 1. Precious scissors, so 1, -1. Similarly, we do the rest. This is 0, -1, 1, comma -1. Now, this is probably one of the very few 3x3 matrix games which you are going to encounter, because normally you will not find too many 3x3 matrix games in your syllabus. This game, let's assume, let's see, I just want to keep consistency of what we are doing. So now let's assume this is player 2. Oops. As usual, this is player 2, this is player 1. We are going to take the belief about the other guy, P2's chance of choosing paper as say P, okay? And P2's chance of using scissors as say Q. Flip it, you can choose any one of these as P, the other as Q, or whatever you like. Because there are 3 strategies, 3 pure strategies, we need to pick a belief about at least 2 of the strategies. So the other guy R can become 1 minus P minus Q. Okay. So this is, like I said, one of the very few 3x3 matrix game that you are going to encounter. Now, in this situation, let me just also spell it out over here. This is going to be 1 minus P minus Q. Just for simplicity, when we are writing it down, it makes the whole thing very simple. If we factorize it in a way that is clear to us, okay? So now we'll do the same thing. What are we going to do? Let's just go over the steps first before I start the calculation. I'm going to calculate the payoff or utility of player 1, each of his or her strategy, rock, paper, scissors. I'm going to write the expected payoff for R and I will take the payoff, taking the probability for each of the other guys' strategies. Similarly, I'll do that for P and S. Then what will I do? I will equate the expected payoff from all the three strategies, because in a mixed equilibrium, mixed strategy equilibrium, the guy P1 is completely indifferent between choosing rock, paper, and scissors. Okay. So what we're going to do is we're going to write expected payoffs. Okay. So I'm not writing, I'm just writing E1P. I'm not writing the whole thing. You can just assume all strategies of player 2 because there are several, and I'm not giving it too much. I don't want to clutter the whole thing. It becomes difficult to understand. So now let's see what happens with rock. The payoff is 0. Probability is 1 minus P minus Q. Okay. Paper, probability is P, payoff is minus 1. Okay. There's probability is Q, payoff is 1. Let's simplify this. This becomes Q minus P. Now we'll do the same thing. Strategy rock. Now, off is 1. Probability 1 minus P minus Q. This one for paper. Probability is P, payoff is 0. Next, probability is Q, payoff is minus 1. Simplify this. Minus Q, 1 minus Q minus 2Q. EU1 results now. And this is minus 1 payoff into 1 minus P minus Q plus 1 payoff into P plus 0 payoff into Q. And this gives me 2P plus Q. Am I right? Or am I not right? This is minus 1. This is also going to be 1 here. Minus 1 is plus P, 2P plus Q. Okay, so 2P plus Q minus 1. Yeah, I think I may have made some mistake somewhere in my previous calculation, but this looks correct to me. Okay, let's check once again if the calculations are correct. I don't know about you, but I usually, in my exams, I used to make calculation errors. My concepts used to be right most of the time. So let me just check it once again. P into minus 1 is minus P, 1 into Q minus P. The second one is 1 minus P minus Q. This is 0, this is minus P. So 1 minus P minus 2Q. Okay. And the last one is minus 1 into 1 minus P minus Q. So this becomes minus 1, this becomes plus P, this becomes plus Q. So this is 1P and this is 0. So this becomes 2P plus Q minus 1. Okay, so now what I'm going to do is I'm going to equate all of these expected payoffs. Okay, and what you can do is that, you know, if you equate the first two equations, let's say, let's number this. This is equation 1, this is equation 2, this is equation 3. From equating 1 and 2 is just a little bit of, you know, around with the equations. Now, if you equate 1 and 2, you will see P automatically gets eliminated from the equation. You get Q minus P is equal to 1 minus P minus 2Q. P cancels out from both the sides. Q is equal to 1. Q is equal to 1 by 3. Now, if you want, you can also solve it, you know, again, equating 1 and 3, for example, say, let's say equating 1 and 3, even though this is a symmetric game, you would have to solve for at least P and Q. The other things you can say that by symmetry, it comes out to be the same. So let's say equating 1 and 3 gives you Q minus P equal to 2P plus Q minus 1. Now, in this case, happens QQ cancels out. In this PP was cancelled out. So you have 3P equal to 1, gives you P is equal to 1 by 3. So what do we get? You see, it's actually, even though it's a 3 by 3 matrix, but the game is like the kind of setup of the game is such that P and Q eventually come out to be 1 by 3, 1 by 3. And you can see that even from the payoffs are 0, minus 1, and 1, right? So net payoff of all three is actually 0. And from that, just from basic mathematical intuition, you can say likely to come out to be 1 by 3, 1 by 3, because 1 by 3, 1 by 3 also gives you like a similar kind of a payoff. and I'm not saying that you do that, you please do solve it, but it just makes sense. P and P 1 by 3. Now, from symmetry applies to P1. Using between P R S and P2's belief about it. Right, so the chances or the probability at which P1 chooses P, R, and S, which P2 will randomly pick any strategy is 1 by 3, 1 by 3, 1 by 3. So Nash equilibrium comes out to be same. Now, this is something you can do in a lot of symmetric games to save your time. You just have to be careful about seeing when the game is actually symmetric and when it is not symmetric. So I hope this is clear. This is a mixed strategy Nash equilibrium. And this is how you approach a 3 by 3 matrix game. It's unlikely that you will be given a 3 by 3 matrix game in which the calculations are way too complex and things like that. It's highly unlikely. But this was a very simple 3 by 3 game. So I wanted to take it in the class. And if you want this game, it's pretty standard. So I'm not really taking it from any textbook. I picked it myself. But if you want to read it, you should be able to find it in most of the textbooks. It's definitely there, I think, in that book, or maybe even our Nash Diction book. So now, this is a very interesting game. Next game, the up, middle, down. This is like a very standard game also, but this is the game which I would like to spend a little bit of time on, and you will understand why very soon. So you see, in this game, what happens is that you want to first always check whether any game has any dominant strategy, whether it has any weakly dominant strategy, is there any mixed strategy, could be dominant or even weakly dominant over any other pure strategy. Now, what do I mean by that? Say, suppose I look at this game. Now, see, in this game, let's look at P1's strategy, up, middle, down. If you look at the strategy middle, against any strategy of P2, middle is never giving a good payoff, right? If P2 is playing L, middle is giving 2, whereas up is giving 3. Similarly, when P2 is playing C, middle is giving 1, whereas down is giving 4. And even the other strategy, which is up, is giving higher payoff than middle. P2 is playing R, middle is giving 0, whereas up and down are giving 1 and 2 respectively. So The only problem we can say would be with L, where middle is giving 2 and down is giving 1, but up is giving 3. What we can see in these kind of scenarios is if I take a mixed strategy of up and down, taking a mixed strategy of up and down, and comparing payoff from that with middle. Suppose I take up and down, just playing around, okay? If I'm taking up and down with half of probability, expected payoff comes out to be 2, which is equal to 2, which is payoff from middle for strategy L of P2. Now for strategy C of P2, what is the expected payoff of up and down mixed strategy? 3, right? 4 plus 2, 6 divided by 2 is 3. That is higher than the payoff from middle. Now if P2 is playing R, strategy up and down in half probability gives me 2 plus 1, 3 by 2 gives me 1.5, which is higher than middle. That means that the mixed strategy up plus down is dominating or weakly dominating the strategy middle. Now let me write this down properly in the game form. So let's go to this. Okay. It's a very interesting game, and some of the books would have this game. Maybe not exactly this, but similar. Okay. Let's open the game table. Yeah, so this is 3, 2, 1, 3. Zero, 3. All right, this is your game table. And what we contend is that the strategy up plus down, the mixed strategy up plus down is weakly dominating middle. So what we are going to do is we delete the strategy middle, because middle is definitely not giving us a great or higher payoff any scenario, right? What we are studying now is called iterated deletion of dominated strategies. And this is something you're actually going to study in the next class, but it is used heavily in mixed strategies, which is why I'm discussing it now also. If you want, I'll discuss it again in the next class, but important to understand this to tackle some of the games which look very difficult, but they're not actually difficult. So, called iterated elimination of dominated or IEDS. Some people call it iterated deletion of dominated strategies, IDDS. It's the same thing, okay? Nothing very fancy. So what we do is we deleted the middle strategy now, which means we know that the player, one is never going to play middle. So, we don't really need to consider that in the game at all. It's as if that strategy doesn't exist, right? That's what we mean by elimination. Now, if the guy P2, so now see, all these payoffs are known to both, right? So P2 will also know that P1 is never going to play this strategy, M, because it's always giving it a lesser payoff than this mixed strategy up and down. So we delete M. Now what P2 will do is P2 will want to compare its own payoffs in this scenario after deleting M. Remember, this is after deleting M. If you keep M in place, game is different from the payoff perspective. But once you delete M and you assume there is no such thing as M, then you compare P2's payoff and you see its payoff. For example, like, when you take U, if P1 is playing U, P2 is getting a payoff of 2 from L and 3 from R, but only 1 from C. And when P1 is playing D, P2 is getting 3 from L, 2 from R, and 2 from C. So the mixed strategy, or you can say a combination of L and R, is weakly dominating C in a similar way. So that means that P2 will always prefer to play a combination of L and R rather than C, because it's giving it a payoff equal to or higher than what it is getting from C. We can similarly delete C also from the game. This P2 is to choose to play that strategy. It's not giving it a good, right? So essentially what happens is that now this game has only 4 strategies left to each for each player. So this game reduces to rewrite the new game. You see, it reduces from a 3x3 matrix to a matrix. What is this? 3x2, 3, 2, 1, 3. 1, 3, 2, 2. This is the reduced game, you can say, what the game reduces to. So now you have a much simpler game. And in this, now you can similarly take probability P of R, and you can take probability Q of D, or whichever way you like. I'm just using the terms I usually use, but you can use some other terms. You can use P and P star or P prime or whatever you like. Term doesn't matter in this particular case. All right. And we find the same method. We use the same method to calculate expected payoffs of P1 and P2. So very quickly, let's write down expected payoff of 1. Then it is using the strategy 2 as 3 into 1 minus P plus 1 into P is P. Expected payoff of 1 when it's playing down as 1 into 1 minus P to P. In S and E, both are equal. You get what? 3 minus 2P is equal to minus P. It becomes 2 is equal to. Okay, I have made a mistake somewhere. It can't be 2. Half. P should come out to be half, but let me once. This part is correct. Plus 2P minus 2 is equal to 1 plus P. Actually, this is wrong. Sorry. This is equal to 1 plus P. 3 minus 2P is equal to 1 plus, now this is 2, this is 3P is equal to 3, right? Yeah, 2 by 3. Okay. So we know P, and now we can use the same methodology to calculate Q. So let's do that very quickly. Expected payoff of 2, say strategy L is into 1 minus Q plus 3Q. Similarly, we write for R, P into 1 minus Q to Q. We simplify this to minus Q, sorry, plus Q, and 3 minus Q. And we equate both. And therefore, I'm just doing it very fast. You don't have to do it that fast if you don't want to. Take your time with it, but not writing all the steps, and in MCQ it does not matter if you write all the steps, but if you're actually appearing for an exam or something, written exam, subjective exam somewhere, you will need to write the steps. So please don't skip the steps. You can say at SNE. So this is how you calculate a game where the MSME of a game where you have mixed strategies dominating some pure strategy. Okay. So what we did was iterated deletion of dominant strategies. Remember, in this case, we first deleted M. After deleting M, we found that C was dominated by a combination of L and R. So in that situation, it makes sense. But if we had not deleted M, it was not dominant, which is why it's called iterated. You cannot delete all of them at the same time. Sequentially keep deleting the strategies. Okay, so this is the famous up, middle, down game. Go back. Found this equilibrium. Now we come to the penalty kick. Now in the penalty kick, you have to do something slightly similar so that you can make your life a little bit easier, and you can perhaps find out whether some strategy is dominated or weakly dominated. So a lot of times when you're given a 3x3 matrix game or a bigger game, the chances are high that you need to find some dominated strategy and eventually eliminate it, because usually that is going to be the case at your level. It's not always. Not always. Like in rock, paper, scissors, there was no dominant strategy or even a weakly dominant strategy, even in mixed strategy. But in many games, that is going to be the case. So penalty kick is one game. Now, I'm not going to solve the whole penalty kick game because it's very similar to what we just did in the up, middle, down game. I'm just going to go over how we approach it, and I will post the solution later on. But I would like you to solve this game on your own. And the payoffs are slightly different from what is there in your exercise. That's why I discussed this game here. But you don't, have to stick with the payoffs. Payoffs are not sacrosanct or something. Okay. In this case, as you can see, this is a constant sum game, not zero sum, but constant sum game where if the payoff of the kicker is 0.4, the payoff of the goalie would be 0.6. You can also frame it in a way as 4 minus 4, 5 minus 5, things like that, which is, I think, how usually it's given like that in your text, but it can be formulated in this way also. It's very common. Let's see, in this game, let's look at the strategy. Capital M. Capital M, compare capital M with the mixed strategy L and R. Capital L, capital R. Okay. Now let's see, the payoff from capital M to kicker is 0.5. And if you take a mixed strategy L and R, and if you just take it just for infusion purpose, let's just take it as half and half. 0.9 plus 0.4 is 1.3, and you divide that by 2, you get 0.65, right? So the payoff is higher than M. Now we go to the strategy small m by the goalie. For that, what does M give? 0.2. And what do capital R, L and capital R give? 0.5 each. So the expected payoff is 0.5. Next one, smaller. For that, capital M gives 0.5 and capital L and R together as a mixed strategy give you 0.6. Means that mixed strategy capital L and R giving a higher payoff than M. We can delete M. Delete M. And now if we calculate the payoffs for the goalie, it will not be exactly the same. Okay, let's say write down the payoffs 0.5, 1, 0.5, 0.8, 5.1, 5.7. These are the payoffs of the goalie, right? What I've written in ink. So now, which strategy is looking like it is, not doing too good. Is there any strategy which is looking like it is not too good? Let's see. We don't know. Let's see. So mixed strategy, small L and small r is not doing better than capital M, right? The mixed strategy, small L and small m could be doing better, but it is not. So as of now, we don't find any mixed strategy which is dominating pure strategy. If you have any doubts or any questions, or if you think there is something else which could be dominant, we can discuss it. Even if you take capital small L, small r as a mixed strategy, it is not dominating small m. Small L and small m, if we take as a mixed strategy, it is not dominating small r. You can take it in a different proportion also if you want. You can take proportion, say 1/3, 2/3. And let's see, is it going to work? No, because for the last column, it's not going to work. So let's just go with the fact that maybe there are no dominant strategies, no mixed strategies which are dominating over any pure strategy. Now you have a 2/3 matrix game, and you can solve it in the same way as we discussed earlier. I will post the solution, of course, but I want you to just have some practice of dealing with these type of games. Now there is a lobbying game. This is the next game I'll discuss. After this, there is one more game, and I don't know, maybe we will not have time to discuss both the games, to solve both the games, but I will definitely post a solution. But in this one and the next game, my main attention is not on solving the game, but more towards how do you write the game table for this kind of a game? Because these type of questions usually require a little bit of thinking in terms of how do you write the game table, okay? Because you have to read the language, and from the language you have to formulate the game table. And a lot of times people make a mistake just in the game table itself. The game table is wrong, your solution, Nash equilibrium, strategy, everything will be wrong. So very important to understand how to write the game table. Now let's see. These are two firms. Okay, this question is about two firms which are trying to decide whether they should lobby the Congress. Here, the Congress is referring to the U.S. Congress, not India. This is an American author. So, should they be lobbying the Congress in favor of a particular bill? Now, this bill is going to favor is some bill which might be useful for these firms. But what happens is that if both the firms lobby, the Congress's decisions are enacted, and then they don't do anything. If none of them lobbies, the profit is 10. And if both of them lobby, it is -5, right? That's what it says. Each firm earns a profit of 10 if none of them lobbies, and -5 each if both choose to lobby. If only one firm lobbies, its payoff is 15. Since it is the only beneficiary of the policy, I'm lobbying and the other guy is not lobbying, only I get the benefit. It's not that they will also get the benefit, because I'm trying to contest the bill in some way. Is not favoring me. And if the other guy lobbies and I don't, my payoff is 0, but the other guy gets 15. Now we want to find the pure strategy and mixed strategy, Nash equilibrium. So this is kind of like the game. I'm just writing it in a rough way here. So these are the two strategies, right? Lobby, not lobby, lobby, not lobby. Let me write it here. Why am I messing this up? Okay. Let's write a These are the, this is firm 2, this is firm 1. What we were told is that if both the firms lobby, they both get -5. If one is lobbying, the other is not lobbying, the guy who's lobbying gets 15, the other guy gets 0. Not lobbying and the other guy is lobbying, I get 0 and 15. If both choose to not lobby, get 10. So this is kind of simple, but you have to kind of understand how to put these values correctly, because sometimes people make mistakes just creating the game table itself. Okay, so let's go back and check if we are correct. So this is the game table. Let me clear annotation. Yeah. So if both are lobbying, their payoff is negative. If both are not lobbying, they get 10-10. But if one is lobbying, the other is not lobbying, the guy who's lobbying definitely gets a much higher payoff of 15. So what is going to be the Nash equilibrium? Let's see. If I am lobbying, the other person will choose to not lobby. If I am not lobbying, the other guy will choose to lobby. The other guy is lobbying, I will choose to not lobby. If the other guy is not lobbying, I will choose to lobby. So this is, if you can see, this is like very similar to the straight swerve game which we had discussed earlier in the class, right? This is an anti-coordination game. And this is like, pretty much, if you get here, if you're able to write this game table and if you understand this is an anti-coordination game, much of the problem is already kind of solved. And you can solve this the same way as we did the chicken game. The payoffs are of course different, but the setup is kind of the same. We will find a pure strategy equilibrium, which is given by lobby, not lobby, not lobby, lobby, right? And you will find a mixed strategy equilibrium in which we can take some probability P and Q for any strategy for F1, F2, and we can solve for P and Q and report that as a mixed strategy equilibrium. So I'll pose a solution for the question, but I would like you to first attempt it yourself, because we have discussed this in the chicken game earlier in the class, and it's like a good practice for you to try it out. Okay. Let's go to the next question. This is a slightly long question, but it is an important category of things. So in this, there are two competing firms in a declining industry that cannot support both the firms profitably. All right. Now, each firm has three possible choices, as it must decide whether or not to exit the industry immediately. That is E. You can call that a strategy E. Whether it should exit at the end of this quarter, T, or at the end of the next quarter, N. The firms have three strategies, E, T, and N. If a firm chooses to exit, then its payoff is 0 from that point onwards. All right. So if I exit now itself, my payoff for all the 3 quarters becomes 0 because I'm not operating. So I don't have any payoff. Every quarter that both firms operate yields a loss of -1, and each quarter that a firm operates alone yields a payoff of 2. So if both the firms are operating in a particular quarter, the payoff to both the firms is actually a loss of -1. Whereas if one firm has already exited, then for the other firm, the payoff becomes 2, and for the first firm, it is 0. For example, firm 1 plans to exit at the end of this quarter, while firm 2 plans to exit at the end of the next quarter, then payoffs are -1 and 1, because both firms lose -1 in the first quarter, and firm 2 gains 2 in the second quarter, right? So in the first quarter, both are operating, so both get -1, -1. At the end of that quarter, firm 1 is exiting, so its payoff remains -1. But for the second firm, because it continues to operate in the next quarter, it gains a payoff of 2. So 2 minus 1 becomes 1. So its net payoff becomes -1, 1 for both the firms. Payoff of each firm is the sum of its quarterly payoffs. This is an important point. It is not just the payoff of that quarter. We are taking the sum of the payoffs across all 3 quarters. Okay. Now we want to find pure strategy and the mixed strategy Nash equilibrium. So I'm just going to give you 5 minutes to go through it, read it again, and then we'll make the game table and we'll discuss how to solve the problem. Okay, so let's see what the game table looks like. This is what the game table works out to be. Let me just explain it once for those of you who might wonder where these payoffs came from. Now, if both the firms exit immediately, that is E comma E, payoff is 0 comma 0 because they're not operating, so payoff is 0. F1 continues in this quarter, F2 has exit already, its payoff is 2 because it's gaining all the profits. So 2 comma 0, the other firm is not operating, and if it continues to operate in the next quarter also, payoff is 4 comma 0. Similarly, for firm 2, you can see if firm 1 has already exited, then its payoff, if it exists in first quarter, E is 0 comma 0. Next quarter or this quarter is 0 comma 2 and then 0 comma 4. Right? It's symmetric. Both the payoffs are very symmetric. If both the firms continue to operate or in the first quarter and exit at the end of this quarter, if you look at T comma T, then they're going to exit in this quarter. The payoff is going to be -1 comma -1. So they're gaining a negative payoff of -1. Whereas if only one is exiting, if firm 1 is exiting in the next quarter and firm 2 is exiting in the T quarter, let's call it T quarter, then firm 1 gets a payoff of 1, whereas firm 2 gets a payoff of -1 because it is already stopped operating at the end of T quarter. So in the next quarter also, it's going to have the same payoff -1. If both of the firms operate for 2 quarters, T and N, they both get a payoff of -2 -2 because they get -1 payoff in the first and -1 payoff in the second. We now mark what happens in the case of a pure strategy Nash equilibrium. Is there a pure strategy Nash equilibrium? F2 is playing E, my payoff is highest for N. If F2 is playing T, my payoff is still highest for N. If F2 is playing N, then my payoff is highest for E. Then I'm better off exiting now itself, right? Let's look at it the other way around. If F1 is playing E, the payoff of F2 is highest for N. If F1 is playing T, payoff of F2 is oops, it's still, oh God, still highest for n. And if f1 n, then f2 would much rather exit now itself, which is 0. So you have two, two pure strategic equilibria, which is n, comma e, and e, comma n. Now you can see that T, the strategy T, is not going to be played by anybody, right? T is weakly dominated because in no scenario is P giving a higher payoff than E or N, right? It's weakly dominated by a combination of E and N. So the strategy T can be eliminated for both F1 and F2, right? In no scenario in the game, if you look at the mixed strategy game, is T giving a higher payoff. It may be giving an equal payoff. Say suppose if F2 is playing T and F1 is playing, actually even then F1 is still getting the highest payoff for N, right? T is not giving a higher payoff in any scenario ever. Okay, so T can be eliminated, and that reduces this to a 2x2 matrix game. Now, a much simpler game, it becomes a 2x2 matrix game for which you have, it's like pretty much like a simple anti-coordination game. Again, say I write down the reduced game table. So that one, four. Goes on, -2 matrix 2, right? Okay, so this is your reduced game. This is fairly easy to solve. You take this as P, this as Q, and you solve for the mixed strategies. I will post a solution for this also, but I would really much prefer it if you can try to solve it yourself first. Okay. So let's come back to what we discussed today, or wait, let me share one more thing. So at the end, given a reference reading, and I'm going to be adding this reference reading in every class because it may vary a little bit from one class to the other. I have added 2 books in this particular section or in this week. Book number 4 and 5. Book number 4 has a lot of exercises for all sorts of games. It's by Felix Munoz Garcia, Daniel Toro Gonzalez. It's a book with just a lot of games and solved examples. So it's a really good book. And the 5th one, it's a free book actually. It's a book under Creative Commons. It's an online book, so you can easily access it. There's a PDF version also available for those of you who want it. It's an Introduction to Economic Analysis, version 1 by Preston McAfee. And I have linked it to the chapter on mixed strategies. So if you want to read like a very concise but very good explanation of mixed strategies, this is probably one of the best readings for that. So we can end it here. I think we've covered almost everything in this particular chapter in this week. And both of your assignments are due tomorrow. So please remember to submit your assignments. And after the due date of submission of assignments is over, I will discuss any problems, anything you may have had in the assignments in the next week. Okay? So thank you, everyone. And we'll meet again next week.